Hi guys. So this is lecture 14, I think. We're done with probability and statistics. So we're going to start the chapter about inverse theory. Well, to understand inverse theory, we have to know some basic concepts of linear algebra. Assume that you might have seen some of these concepts in either geometry or calculus or pre-calculus, but this is going to be a pretty detailed review since there are also some undergraduates in the class. So first of all, we're going to start with the concept of vector. So this is the review of linear algebra. And first, we're going to discuss vectors. So in mathematics, a vector is a geometric object that has magnitude or length and direction. Vectors can be added to other vectors according to vector algebra. A Euclidean vector is frequently represented by a line segment with a direction, or graphically as an arrow, which connects an initial point A to a terminal point B, and generally we indicate this as V. Sometimes to indicate that this is a vector, we're going to put we're going to underline it. And so this is essentially an arrow. This one here has a length, which is generally the magnitude of the vector, and it has a direction. There is a bijective function between points in the Euclidean space and vectors. So typically, if you have the Cartesian plane and you take a point here, this one here has coordinates x and y, or let's say x1 and x2. Then this point P is determined by the coordinates x1 and x2. But we can also see it as a vector that has origin in that starts in the origin and ends in the point P. So the vector V is the segment OP vector. And there is a bijective function that links the coordinate to the point to the vectors. This function is the coordinate function. So, namely, the coordinate functions. Well, we can think about vectors in a multidimensional space. So a vector V in an n-dimensional space can be represented as with the coordinates v1, vn. So to be precise, these are called the coordinates with respect to the canonical basis of Rn. Now, we can define the norm of a vector. So the norm of v is the square root of the sum for I that goes from 1 to n of vi square. This is also called the Euclidean norm. It's not the only norm that we can define, but this is the one that we're going to use the most. We generally say that this norm induces a distance, which is called the Euclidean distance. So let's look at the specific case of R2, which is sometimes indicated as R times R. So here we take 2 points in the Cartesian plane. So this is XA, this is XB, this is YA, and this is YB. This is the point B, this is the point A. So if we want to define the distance between A and B, we're going to use the usual Pythagoras theorem. So the distance between A and B is the square root of the sum of the segment, let's call this point H. So this can be defined as the square root of AH squared plus BH squared, which is also equal to XB minus XA, so the difference in the coordinates in the x-axis, along the x-axis, plus YB minus YA square. Well, this one here is the norm of the difference B minus A. This is not the only distance. We can define other distances, but this is the one that we're going to use, that we're going to commonly use. So we're going to use the Euclidean norm and the Euclidean distance most of the time. So we have a vector, which is an object, a geometric object, uniquely defined by the coordinates of a point. The norm of the vector is the square root of the sum of the squares of the coordinates. And the distance between 2 points is the usual Euclidean distance that is defined by the Euclidean norm. Now, there are other types of distances. For example, we have the Manhattan distance. It's called Manhattan because it looks like the way we move around in New York. Instead of going along a straight line between A and B, we first go along one direction and along a straight line in one direction and then in another direction. It's like walking around blocks. So in this case, the distance, I'm going to put an M here to say that it is the Manhattan distance between A and B is equal to the absolute value YA minus YB plus the absolute value of XB minus XA. So it's this distance here plus this distance here. So the corresponding norm is actually the norm of x is equal to the sum for i's that goes from 1 to n of the absolute value of xi. This is also called the L1 norm. This is also called the L2 norm. So if we have, for example, the distance between A and B can be written as the norm of A minus B, which is the sum for i's that goes from 1 to n of xi of B minus xi of A. So this one here is generalized in an n-dimensional space. Now I'm going to give you a couple of other definitions. We're going to define a vector space. Sorry, a vector metric space, or simply the metric space. This is a vector space where we define a distance and then we have a norm space which is a norm space is a vector space where we define a norm. Well, for example, Rn or R2, these are examples of, they're both metric spaces and norm spaces. A metric space is also a norm space, but the vice versa is not necessarily true. So in general, we say that the norm induces the distance. So in general, we can define a distance between a point x and 0 as the norm of x. And depending on which norm you choose, we're going to have different distances. So examples of norms, we said we have the L1 norm, which is the sum for I that goes from 1 to n of the absolute value of xi. We have the L2 norm, which is the usual Euclidean distance, the sum for I that goes from 1 to n of the square root of xi. Sorry, of the square of xi, and then everything is under square root. We also have the L infinity norm, which is the maximum for i's that goes from 1 to n of the absolute value of xi. This is important because this ones here, they define different distances. So for example, if we look at a Cartesian plane and you want to represent all the points with distance 1 from the origin, in the L1 norm, it's going to be something like this. So this is -1, this is +1, this is +1, this is -1. So these are all the points such that the norm L1 is equal 1. Then we have the norm L2. Well, this one here is something that you should be familiar with. It's typically circle. So this is 1, -1, 1, and -1. So these are all the points such that the norm L2 is equal to 1. Well, in the norm L infinity, so we just take the maximum in each direction, so we're going to have a square. So these are three different types of norms, and they induce three different distances. The first one is defined by the sum of the absolute values of the coordinates. The second one by the sum of the absolute values of the squares of the coordinates. Since you're taking the square, there's no need to take the absolute value. And then the third one is defined by the maximum of the coordinates. Now, let's say that we have two different vector spaces, and we want to define an operation between one space and the other one. So let's say that we have V and W that are two vector spaces. Then an operator F is essentially a relationship between V and W that associates to an element X in V an element Y in W. A function is in the set of real numbers is a special case of an operator. Now, for what we're looking at, we're mostly interested in linear operators. So we have our vector spaces. And again, most of the time, these vector spaces will be the set of real numbers, either in one or multiple dimensions. And then we have an operator F that associates to an element X in V and element Y in W. Now, F is linear if f of x plus y, well, I should actually use different, let's say x1 and x2, plus x2 is equal to f of x1 plus f of x2 for every element x1, x2 in the set in the vector space V. And then f of alpha x is equal to alpha f of x for every vector in V and for every alpha in the set of real numbers. So x is a vector, alpha is a scalar. Now we're going to talk about vectors and matrices. And here we have some definitions to talk about. First of all, we have a set of vectors v1, vn. So these vectors are said to be linearly independent. Are linearly independent if once you take a combination CV1 plus C2V2 plus CNVN equals 0, implies that the vector C equals C1 Cn is the vector 0. So each component C1 Cn is equal to 0. Let's look at an example. So let's say that we have V1 and V2 in R3. So V is simply 1, 2, and 3, and V2 is 4, 8, and 12. So this is pretty easy. It's hard to represent, but so V1 would be, so let's see, let's say that this is x1, x2, and x3. So 1, 2, and 3, so it would be approximately here, assuming that this is a 3D projection. And V2 would be approximately here. It's not really on scale. So here we have, it's hard to plot, but here we have our vectors V1 and V2. This is the point P1 equal 1, 2, 3. And this is the point P2 equal 4, 8, 12. Okay. Now, it's obvious that V2 is equal 4 times V1. So this means that 4 times V1 minus V2 is equal to 0, which means that C1 is equal 4, C2 is equal minus 1. So V1 and V2 are not linearly independent. Okay, there's another definition that I need you to remember. So this is the definition of linearly independent vectors. This is the definition of basis. So we have a set of vectors v1, vn. So v1 and vn is a set of bases for a given vector space V. If they are linearly independent, and every vector in V can be represented as a linear combination of v1, vn. So these two conditions, they're generally summarized as if V1 Vn is a linearly independent spanning set. Which means that they are linearly independent and every vector in V can be expressed as a linear combination of V1, Vn. So again, we're going to look at an example. In R3, which is the same example with the same dimension that we have seen here, well, a basis is given by E1 equal to 1, 0, 0, E2 equal 0, 1, 0, and D3, which is 0, 0, 1. So essentially, this vector here, and this vector here is a basis for R3. In general, okay, so let's look at matrices now. So a matrix is essentially a rectangular array of real numbers that are arranged in sets of m rows with and n columns. So a vector is simply a matrix consisting of a single column. So this is essentially, well, there's not really a formal definition. I guess that it's a rectangular array of real numbers. They can be complex too, but arranged in sets of m rows and n columns. So essentially, you can write a matrix as a table where here you have the element A11, here you have the element A12. So the first subindex is the number of the row and the second one is the number of the column. So this is A1n and this is A21. This is going to be AM1 and finally this is going to be AMN. Now you can write a vector as x1, xn. So this would be a matrix of size 1 times n. So this is a matrix of size m times n. And the vector is a matrix of size 1 times n. Then you can have square matrices where m is equal n. You can have diagonal matrices where all the elements that are not on the diagonal are equal to 0. So we say that Aij is equal to 0 as long as I is not equal to j. If I is equal to j, the element is on the diagonal. So something like this, A11, A22, ANN, and zeros otherwise. Well, this would be, for example, well, it looks like 3 by 3, but it can be any dimension you want. You can also have matrices where you have the diagonal, the upper diagonal, and the lower diagonal, so a sort of 3 diagonal matrices. These are not 0 on the diagonal, upper diagonal, and lower diagonal, and they're 0 everywhere else. You have sparse matrices. This is important if you like to program a lot, because sparse matrices means that a lot of elements are zero. So most of the entries are zero. So when you do, but they're not organized along the diagonal or on a specific order. This is important when you do programming because you want to save space. Matrices can be pretty big to store. So if you only saved the locations where you have known zeros, you save some space. You can have upper triangular matrices and lower triangular matrices where whatever is above the diagonal or whatever is below the diagonal is zero. So upper triangular matrices, it means that aij is equal to 0 when I is greater than j. And then lower triangular matrices, it means that aij is equal to 0 if I is less than j. So these are in the form, say, a1, 1, ANN, and then here you have something like aij, and then here you have 0, or vice versa. So this one here would be upper, this one here would be lower. Okay, so we talked about vectors, we talked about functions or operators, and we talked about matrices. Now, I would like to find a smart way to put everything together. So let's say that I'm going to change color just because this is something that probably you haven't seen very often, but unless you have taken a linear algebra class. So if you say if you have an operator from the set of the multidimensional space, n-dimensional space of real numbers, and into the m-dimensional space. So this one here associate to EI, which is the canonical base. We define that here for a three-dimensional space. If you had a space with a higher dimension, this would look simply like a bunch of vectors EI for I that goes from 1 to n, and then EI, for every I, EI is equal to a vector which has a 1 in the I position. So this is the specific example for n equal 3. Okay. So if you have an operator that goes from Rn to Rm, and that associates to the canonical base some elements a j for j that goes from 1 to m, or with another notation you could write f of ei is equal to ai1 I have an issue with I and 1, as you notice, because the Italian version would be, it's not just a straight line, and they try to use the American version. So this is AI1, and this is AIM. So essentially, you're taking each of these vectors here, and you're associating some coordinates in a different dimensional space. So this one here is a linear operation, and it can be summarized with a matrix. So A equal A11, A1n, AM1, and AMN of dimension m times n. And this one here is the matrix associated to the linear operator f. You will see that using it is much easier than discussing it in theory, so I wouldn't worry too much about understanding the formal aspects. It would be nice if you could, but in many of your applications you won't have to. Okay, so typically we're going to see this when we study inverse problems. So these definitions are going to be useful. So we have say an application from Rn to Rm, and these applications here takes, or operator and application are synonyms in this case, takes V and associates a vector W. Okay, so V is a vector in Rn and W is a vector in Rm. It's easier if you think about that in a two-dimensional space. For example, you can take a vector in a two-dimensional space and map in a three-dimensional space, or maybe R3, R2 is easier. You have a vector like this. If you take the projection on the XY plane, you're going to get a vector like this. So this is V and this is W. The projection is an operation that goes from R3 to R2. Okay, this is an example of operator. Anyway, I have to introduce some definitions that we're going to use. So this is going to be, for example, x1, x2, x3. We're going to, I'm going to introduce some definitions that we're going to use, probably not like next lecture, but in the one after it. So we have the null space. So the null space of an operator f is equal to the set of vectors in R such that f of v is equal to 0. Now v is always a vector. I should be more careful with the notation. In this case it's obvious because we have specified the dimension of the space, and so this one here is the null vector. So which components are all equal to 0. Okay. Well, this is not necessarily just 0, right? It's not just v equals 0. It could be a set of different vectors. For example, in my previous example, if you take all the vectors with different length, so for example, you take all the vectors with different length along the, or height if you want, along the third direction, and you take the projection, they're all going to be projected in the vector 0. So this v, I'm going to call it v1, v2, v3, all these vectors belong to the null space. And then we have the range or image. These are just two different names of the same thing. So the range of f or image of f is the set of vectors W in Rm, which is the space where we're mapping into, such that there is a v, a vector v in Rn, such that f of v is equal to W. This is something that you have probably seen before in a less formal way, or in a simpler way. So you have two sets, for example, of points. So let's say that this one here goes into this one here, this one here goes into this one here, this one here goes into this one here. So this would be the domain of the function. And now this subset that I'm going to do with a different color, or I'm going to point them with a different color, these are going to be the elements that belong to the range of f or the image of f. Now, you can actually define that for matrices too. So if A is the matrix associated to F. Then the null space of A is the space of the solutions well, before I write it down, let's see what the null space of F would be. So A is the matrix associated to F, right? So the null space of F is the vectors in Rn such that f of v is equal to 0. But if F is a linear operator, and A is the matrix associated to F, writing f of v equals 0 is equivalent of writing A times v equals 0. So this is the space of F solution of A times v equals 0. And this is a linear system. So we're going to look at linear systems in a minute. And then the range of A is this space generated by the columns of A. Okay, so with matrices we can define operations. Now the sum is well defined. So if you take A plus B, it's simply the sum point by point. Well, if they have the same dimension. Now, the product is a little bit tricky because A times B can be done if the number of columns in A is equal to the number of columns, so this is going to be the condition, the number of rows in B. This is not a product point by point. This is called the dot product. And in general, A times B is not equal to B times A. Also, A times B equals 0 does not imply that A is equal to 0 or B is equal to 0. And the way we do the product is as follows. So this product here is the product of, let's say that this one here is a matrix m by n, so m rows and m columns, like we have seen before. So this is n, m, n. And this one here is going to be B. So in order to be able to make the product, the number of rows in B has to be the same as the number of columns. So this one here has to be n times, I'm going to write P. So this is B1, 1. This is BP1. This is BN1. This is BNP. Now, the product is going to be a matrix C. So this one here is going to be equal to C, where C is of dimension m times P. And the way C is constructed is that the first element, C11, is going to be built like this. You're going to take the first row of A, you're going to multiply point by point by the first to the first row to the first column of B, and you're going to sum all the elements. So C11 is going to be equal to A11 times B11 plus AN1 times BN1. So this is C11. Then we're going to move to the next element. So this is going to be, I'm going to use a different color, C12. Well, we're going to take again row number 1 because we're looking at row number 1, but now we're going to take column number 2. And we're going to do exactly the same procedure. And so on and so forth. This is called the what we're doing is the dot product between rows of A and columns of B. So this is the dot product of rows and columns. I assume that most of you were familiar with the dot product, but geologists might not be. Well, undergraduates in geology probably are not. So I'm going to give you the definitions here. So you take two vectors in the set of say Rn. Now the dot product x times y is equal to x1 times y1, well, I don't need the parentheses, plus x2 times y2 plus xn times yn. So remember that I told you about the norms in metric spaces. Well, the dot product induces a norm, and it is the Euclidean norm. So if you take x in the set of in Rn, now the norm L2 is equal to the square root of the dot product x times x, which is equal to the square root of x1 y1 plus xn yn. Sorry, it's x times x, so this is going to be x1 x1, this is xn xn, so this is the square root of the sum of xi squared for I that goes from 1 to n. So by using the definition of the dot product here, we define the norm L2. So when you are in a multidimensional space, you can define orthogonal vectors. Well, we know how to do it in R2. I'm going to show it to you in a minute. So if you have x and y in Rn, these are orthogonal. We generally say x is orthogonal to y if the dot product is equal to 0. In R2, it's the typical definition of orthogonal vectors. If you take the dot product of these two vectors, this one here is something in the form, so we call this one here x. Well, let's call this one here x and this one here y. Well, x is of coordinates x0 and y is of coordinates 0, y. Well, if you take the dot product, this is going to be equal to 0. And indeed, this is these are two orthogonal vectors according to the usual definition of orthogonality that you have seen in geometry, probably in high school. The dot product has a different notation too. So I'm going to write it here. Some people, they use a parenthesis, x comma y. This is a different notation. The key point is that this quantity here is a scalar. So you take two vectors and their product is a scalar. That's the dot product. So I'm going to write it as a note or result that we can derive. So if you take a vector in the null space of a matrix A, then it means that by definition that A times X is equal to 0, right? But this one here means that X is perpendicular to each vector of A. So of each row of A. Because you take the matrix A, you multiply by a vector x1, xn. It has to be a column vector, otherwise we cannot do the multiplication. Now, this one here is equal to the null vector by definition of belonging to the null space. So this means that if you take the first row of A and multiply it by x, you're going to get 0. So this scalar product of the first row of A times x is equal to 0, which means that x is orthogonal to the first row of A. And you can do it for each single row. It also means that, well, when we talked about matrices, I forgot to mention that we can also work with the transpose. So I'm going to write it here. If you take A transpose, you're basically switching the rows with the column so that, well, this is not going to fit. So I have to write it somewhere else. Well, I guess, okay, I'm going to write it very small. If you take the transpose of A, you switch the columns and the rows. So what you get is a matrix of size n times m. So the diagonal is always the same, but then what was A21 becomes A12. So A21 goes here and A12 goes here, and so on and so forth. So this one here is going to be AMN. Well, NM. Okay. Okay, so if we take the transpose of A, then it means that X is also perpendicular to each column of A transpose. And so we conclude that the null space is orthogonal to the range of A transpose. Remember that the range is the space generated by the columns of the matrix, so in this case A transpose, and null space is the space such that A times the vector is equal 0. Okay, the range of A, I go back to the definition of range, is the space generated by the columns of A. So what that means is that the range of A is the set of elements B in Rm such that it exists an X in Rn such that A times X is equal B. Okay, this is what space generated by means. So this means that A times X equal B has at least a solution. But this is what we generally call linear systems. And it means that B can be written as a linear combination of A. So this is essentially what we're going to do when we discuss inverse theory. So an inverse problem can be written as Gm equal D. D is something that you measure, the data, and M is the model that you want to estimate. For example, D could be seismic velocity, and M could be porosity. So what we're interested in is finding a solution M so the goal is to find a solution M of the inverse problem. So in a sense, the range of the matrix G. Okay, so this is the range. The reason why I discussed that is that I would like to give you another definition, and then I think we're done with definitions today. And this is the definition of rank. So if you have a matrix A of dimension A to M times N, then the rank of A is the dimension of the range, of the range of A. So the rank has to be less than the minimum between M and N. If it is less than, it means that the matrix is rank deficient. And if it is equal, it means that it is full rank. We're going to use these concepts, and when we're going to look at those, I'm going to try to be a little bit more detailed. For those of you who are not familiar with, the other ones can just skip through it. Okay. I think that this is pretty much what I wanted to cover today. I lied to you. There's one more definition. This is the definition of subspace. So it's subspace W of Rn is a subset of Rn that verifies this condition. So the 0 vector has to be an element of W. If you have x and y, two vectors in W, then the sum has to be in W as well. So W has to be close with respect to the sum. And if you have a vector x in W and you take a scalar in the set of real numbers, then S times x must belong to W in order for W to be a subspace. So an example of subspace, well, a plane in R3. If you take a plane in a three-dimensional space, well, this is defined by x1 plus x2 plus x3 equals 0. Well, this is an example of subspace. Now, the null set is a subset of R. Okay, I think I'm gonna stop here. It's a little bit short. I would still have some time, but what I want to cover next time is eigenvalues and eigenvectors. So probably I'm gonna stop here. Well, I guess I can introduce these definitions since I have the time. This is the last topic of the day. So eigenvalues and eigenvectors. Okay, so we start with the definition. So if you take a matrix A of dimension m times n, so A has an eigenvalue lambda and eigenvector x with x not equal 0 if A times x is equal to lambda times x. Some people also write it in the form ax minus lambda x equals 0, or a minus lambda times the identity times x equals 0. This is just this is just a different notation, but that's exactly the same thing. So to find eigenvalues and eigenvectors, we solve what we call the characteristic equation. So the determinant of A time minus lambda I, so I is the identity matrix, should have written it here. So you have 1 along the diagonal and 0 otherwise. So we solve the determinant of A minus lambda y minus lambda I equals 0. So we first find lambda, and then we solve the system of equations in X. If we can find a set of n linearly independent eigenvalues xi of A with associated eigenvalues lambda I, then we can diagonalize the matrix. So we have A matrix, xi the eigenvalues, and lambda I the eigenvectors, the eigenvalues. I switched them. So the eigenvalues are scalars, the eigenvectors are vectors. And this is the lambda, the Greek letter. Here, this has to be square. So A n times n. Sorry about that. Well, then we say we can diagonalize A. So the diagonalization of A means writing A as P times capital lambda times P minus 1. So P is simply the matrix where you have column vector x1, column vector xn. So these are the eigenvalues, the eigenvectors, which are written as column vectors. And capital lambda is simply diagonal matrix where the diagonal is lambda 1, lambda n. Well, not all the matrices can be diagonalized. In general, if A is real and symmetric, then there is a diagonalization. That's a specific result. Okay, that's enough for today.